Hello boys and girls, this is the Triple Science Physics Higher Paper 2 Masterclass video. Make sure you're in the right room and listening to the right recording. This is tailored for the Triple Science Higher Paper 2, so it's using the advanced notice to really focus on some of the things that we hope you don't get wrong in your paper. Okay, so just like the previous recording, we want to focus on the colour of the slides. Red slides means that we're listening and we are reading. Okay, we're not talking, you're focused on what I am saying and what the video is showing. Okay, when the video is slides are green, that's when we're reflecting, writing, maybe talking to the person next to us, maybe asking questions to the teacher in the room. Okay, a lot of the time that's going to be fixing the mistakes or filling in the blanks. Okay, so red is listening and reading, green is reflecting and writing. Okay, now the advanced information that hopefully we've all seen is here. What's not going to be on the test is going to be no moments, levers and gears, no EM radiation, no black body radiation, and they won't have anything about permanent and induced magnetism, magnetic forces and fields. Okay, now for this last one, I think they could put in something about the motor effect. That could be on there, but it is not a focus. It's not a focus. It might be there in a small way. That's my guess as what they might put in there that's not on the list. Okay. The major focuses are forces and their interactions, work done on energy transfer, force and elasticity, pressure and pressure difference in fluids, describing motion along a line, momentum, waves in air, fluids and solids, solar system, orbits, satellites and redshift. The required practical, that will be assessed in some way. Okay, I reckon this would be a big part because it's the only required practical that they're saying is on there. It's going to be the reflection of light by different surface types and the refraction of light on by different substances. Okay, so we need to be ready for that. That's what we're looking at first. Now here we've got a simple drawing of a setup of how I would measure and explore the laws of reflection. Okay, so you've got two jobs. I want you to write down what the variables are on your whiteboards or your scrap piece of paper or the back of your exercise books or wherever it is. I want you to write down the variables, and I'd like you to sketch a graph showing the angle of incidence versus the angle of reflection. So I'm going to pause the video now. Okay, moving on. We've got, okay, our variables. Independent variable, the thing we're changing on purpose, is the angle of incidence. The dependent variable, the thing we're seeing if it changes, is the angle of reflection, or how it changes rather. The control variables will be things like the distance of the ray box from the mirror, so how far away the mirror is, the width of the ray. We control that by placing the slit closer or further away from the light source, and the wavelength of light. We're keeping all those the same, okay, but we're changing the angle of incidence and we're seeing its effect on the reflection angle. Now if I was to plot a sketch of results, I should have something that looks like this, where I've got R for reflection, I for incidence, the ray that comes in, the first one. Okay, and my points should be the same. Okay, so first it's a linear graph. As incidence goes up, reflection goes up. Okay, it's directly proportional. It's a straight line that goes through zero. But importantly, okay, for a plane mirror, for a simple mirror, the angle of incidence should equal the angle of reflection. Okay, so what I'd like you to do, I'd like you to draw a ray diagram that shows that. I want you to sketch it with the correct labels. Okay, so pause the video again. Okay, so moving on, we've got the mirror drawn already on for you, and then we've got this dashed line. Whenever we're looking at rays and ray diagrams, this dashed line, this normal line, is really crucial. This is a line that's not really there, that we create to help us measure angles. Okay, it's perpendicular to where the rays are hitting and interacting. So in this case, perpendicular to the surface of the mirror. When we look at refraction, it's perpendicular to the material the ray is going through. But in this case, perpendicular to the surface of the mirror. So we've got the incident ray coming in, and we measure the angle of incidence by measuring from the ray to the normal line. Okay, we don't measure from the ray to the mirror, it's from the ray to the normal line. Okay, and then for the reflected ray, the angle should be from the normal to the reflected ray. Okay, and these angles, theta I and theta R, they should be identical. If it's a flat plane mirror, they should be the same. Now, just to say again, this normal line, really crucial. Now, it's not really there, and that's why it's drawn as a dashed or dotted line. Okay, now when you're drawing these, it's going to be really important that you use a sharp pencil and you use a pencil. Do not use a pen to draw these diagrams. Okay, if you make a mistake with the pen, it will be very difficult to get your marks back. Use a pencil, a sharp pencil, and have a rubber with you for your exam. Okay, it's going to be really crucial. Okay, so next, there are two types of reflection. One is off of smooth surfaces, this is one on the left, and the other is on rougher surfaces. I want you to know the two names, and I want you to try and sketch what type of reflection diagram you might get from a rough surface. So pause the video here. Okay, moving on. So we've got two types of reflection, specular reflection and diffuse reflection. Okay, specular reflection is predictable. It's easy to see that it obeys the law of reflection. Diffuse is not. Because we've got this rough surface, the rays are coming in at a predictable angle. We can measure that angle, but they appear to come off at random angles because the surface is so rough. Okay, the individual rays still obey the law of reflection, but because there's so many different angles on this surface and so many different angled normal lines, it appears to come from lots of different directions. Okay, so specular is predictable, diffuse is not. Okay, now specular reflection happens off of smooth surfaces, so things like mirrors, the surface of really calm, flat water, something that's shiny. Diffuse comes off of rough surfaces like paper, brick, clothes, this wooden fence posts. Okay, because the surface is rough. Right, moving on. Refraction. Okay, I've got a similar diagram to before, but this time it's refraction. A glass block, we've got a ray box, travels through the glass block and it changes direction. I need to sketch a ray diagram showing the diffraction in a rectangular block. Okay, pause the video here, sketch the diagram. Okay, moving on. Here is my simple ray diagram with a glass block, nice rectangular. I've got my incident ray coming in. I have a normal line perpendicular at right angles to the surface. Okay, I'm measuring my angle of incidence from the normal ray to the angle of incident, to the incident ray. Okay, as it travels into the surface, in this case it's glass, it slows down and bends towards the normal. Okay, the angle of refraction here is smaller because it slows down in the glass. We're going to move on to that in a moment. Okay, but this is how we measure it. When it's moving out of the glass block back into air, it will speed up and bends away from the normal. Okay, but the key thing for this little picture is how we're drawing our normal lines, how we're drawing our angles of incidence. Make sure you're accurately writing down those precise labels. Okay, and remember, we're measuring from the normal to the ray. Next job, I want you to try and fill in the missing words in this simple method for setting up our refraction practical. Pause the video here. Okay, so our missing words are, so we're placing the glass block on the sheet of paper, carefully drawing around it using a pencil, switch on the ray block, direct the beam of light at the side facing the block. We mark on the paper a point on the ray close to the block, a point where the ray enters the block, and a point where it exits. Exit, missing word, the block. A point on the exit light ray at which the distance of about 5 centimeters, maybe a bit long, from the block. All these pencil marks are there to try and show accurately on our piece of paper the path the light travels. We draw a dashed normal line, okay, at right angles perpendicular to the outline of the block. Okay, show where it enters the thing. We're removing the block, joining the mark points up with 3 straight lines, so showing the path of the ray. Okay, we're replacing the blocks in the outline and repeating the above steps for each ray striking the block at different angles. Okay, we can then measure those angles with the protractor, and we can look at the change in the angles of refraction to the angles of incidence. Okay, now I said before, refraction is all about change of speed. Okay, so here's just a quick analogy. I've got a car travelling along a pavement, so it's got good grip. Then it's travelling into sand, and the car slows down. So if we look from above, the car's travelling along nice and fast on the pavement. When it hits the sand, traction reduces, the amount of friction is less, the car slows down. Okay, when both wheels hit the sand at the same time, nothing really happens apart from it slowing down. It doesn't change directions. But when it's going at an angle, one of the wheels is going to hit first. This side of the car, the right side of the car, is going to hit the sand first. Okay, when that happens, that wheel slows down. The other wheel is still travelling just as fast. Okay, and that causes the car to bend. So when it's going from fast to slow, it bends towards the normal. What do you think might happen when it speeds up? When it speeds up, the opposite happens. It bends away from the normal. Okay, so you could have a look at this cone. You could just imagine it's reversing. So if it's reversing, the picture looks identical. Okay, the only difference is the direction of the arrows on the rays. Okay, now for refraction, most of the time you will be looking at rectangular blocks, but not always. They could show you a triangular prism. They could show you a semicircular prism. Okay, just a different shaped block. Okay, the process is the same. The key part is knowing how to draw the normal line. The normal line is perpendicular to the surface. Okay, so in the triangle picture here, we've got two lines. These are both normal lines. Okay, it's the normal at this point Q and the normal at point R. Okay, so just be aware that you could get asked for a slightly different shape, a slightly different geometry, but the normal line is always perpendicular to the surface. The same with the semicircle, the normal line looking at what's happening here as it's leaving the glass block. Okay, the normal line is perpendicular to the surface. Okay, and here when we're going in from air to glass, the normal line is perpendicular to the surface. Okay, right, moving on. This is tricky. You need to describe the relationship between the angle of incidence and the angle of refraction. Okay, how would you find the angle of refraction with an angle of incidence of 80 degrees? Be careful with this. Look at the numbers. Pause the video here. Okay, so it is not directly proportional. If I put a ruler along these points, it shows that it is not a straight line. Okay, it is not a straight line. The points curve away. Now, as the angle of incidence increases, the angle of refraction increases, but by a smaller and smaller and smaller amount as my angle gets higher. Now, you don't need to know the mathematical relationship of it once you do A-levels, but you need to know that it's not a straight line. When we're really close to zero, to really small angle of incidences, it approaches a straight line, gets close to it, okay, but it is not a straight line. It is not directly proportional. Okay, so here is an example of a curve that I can fit to this graph, because lines of best fit do not always have to be a straight line. Here is a curve of best fit, my line of best fit drawn on, and I use this to help me draw my, to help me get my angle at 80. Okay, so I can use two rulers. Okay, two rulers. First I'll go up from 80 after I draw my line of best fit, and I go along to see my angle of refraction. Okay, so up from 80 and then along to the left, the angle of refraction, and it's about 42, 43 degrees. Okay, now because this is on a screen, you'll have a lot of leeway in terms of where the numbers are, and even in your exam, because you're using a line of best fit, you're interpreting where this data is going to be, you'll get a little bit of leeway. Okay, but just be careful in drawing those lines of best fit. Use a pencil. Do not use a pen. If you use a pen, it's very easy, okay, to go and make a line of best fit that's messy. And that will make it so much harder to get the correct result. So use a pencil. Okay, right, next job. We've got 6 distance time graphs, 6 motion graphs. You need to say what is happening in each graph. Pause the video here. Okay, moving on. We've got, first graph is stopped. It's horizontal, the distance is not changing. If the distance isn't changing, the thing is stopped, it's not moving. Second graph, as time's going up, distance is going up, so it's got to be moving. Next thing, it's a straight line. This tells us it is constant speed, okay, because for every bit of time it's moving by the same amount of distance. Okay, so a straight line that's increasing is constant speed. The stopped graph is a special case of constant speed. The constant speed is stopped. Okay, third graph, constant speed but returning to the start, it's going backwards. The distance is decreasing as time is going up. It's constant because it's a straight line. Fourth graph, it's accelerating. Okay, it is not a straight line, therefore it must be some form of acceleration. Now here, we're starting flat and getting steeper. If we're starting flat, it's slow, and steeper is faster, so the speed is increasing, so it's accelerating. This case, okay, our fifth graph, we've got time and distance. We start with a high slope, and that slope gets slower and slower and slower and lower and lower and lower until the end, until it looks like it's almost stopped. So this is decelerating. The final graph, we've got time and distance again. Straight line, so it's got to be going at a constant speed, but comparing it to this middle graph, it's not as steep, so it's going slower than B. Okay, now next, we've got the exact same graphs, but they are for velocity. the motion is entirely different. Be very careful. But same process, I want you to try and describe what's happening in each case. So pause the video here. Okay, moving on. So here we've got velocity time graph. This time the velocity isn't changing, it is a constant velocity. Okay, it's not stopped. It's got a velocity, but it's just not changing. So we've got constant velocity, different from the distance time graph. Next graph, accelerating at a constant rate. Okay, the velocity is increasing with time, and it's increasing by the same amount every second, so the acceleration is constant. Last graph, on the top row, we've got a constant deceleration. The velocity is decreasing as time goes up, and it's doing it by the same amount every second. This is the only graph that shows stopped, and it's stopped at the very end when the velocity reaches 0. Okay, fourth graph, we've got increasing acceleration. So at the start, we're relatively flat, which means constant velocity, and it's getting faster and faster and faster and faster and faster and faster as the slope gets steeper and steeper and steeper. Okay, next graph, we've got decreasing acceleration. This is a really important one that we'll come on to in a moment in more detail. But here we start with a very fast high gradient, so the change in velocity is very great. It's getting faster and faster and faster and faster, but that change is getting slower and slower until we get to a constant velocity when it's going flat. The last graph shows that it's accelerating because the velocity is increasing. It's a straight line, so it's at a constant rate, but it is lower than B because the gradient's not steep. Okay, moving on, we've got the other thing you can do with velocity time graphs is find distance. Now you find distance by looking at area. Okay, you look at the area under a distance time graph or a velocity time graph is the distance. Okay, base times height of a rectangle, base times height times by half for a triangle. We can split up all of the velocity time graphs into those shapes. Okay, and you can then work out that distance because velocity multiplied by time is distance. Okay, so we've got a simple graph here with velocity and time. I'd like you to try and map out the different shapes and find the distance travelled by this car journey. Okay, find the area of the graph. Pause the video here, give it a go. Okay, moving on. So I split it into a whole bunch of different rectangles and triangles. We've got area 1, area 2, area 3, area 4 and area 5. I times the base by the height of all the rectangles. I times the base by the height divided by 2, or times by 0.5, or times by a half to get the area for the triangles. I add them all up and I got a total distance of 2,175 meters. Okay, next thing, moving back onto that more complicated accelerating but decreasing rate. Okay, picture here. This is a parachutist jumping out of a plane. Okay, I want you to try and sketch the graph and we try and label what might be behind that describes how the forces are changing and describe what's happening to the acceleration. Okay, so pause the video here, sketch the graph and try and draw it. Okay, moving on. Okay, so I've got a whole number of labels. This is all about terminal velocity and changing drag. Okay, so at the beginning, the resistance is very small, the air resistance, because we're not going very fast. At the beginning, we're going slow. Okay, and the two things that air resistance depend on are the speed. Okay, because the faster you go, the more the air particles or whatever the fluid particles are hitting the object. Okay, the lower the air resistance. So the lower the speed, the lower the air resistance. The other thing that affects it is surface area, which we'll be changing later. So we start with a slow speed, a low speed, so the air resistance is small. So the person accelerates. Weight is bigger than the drag force, so the person accelerates. They get faster. As they get faster, air resistance increases. They're going faster, they're hitting more air particles, so the drag force increases. Okay, that will keep happening until the weight equals the drag force. At that point, when weight and drag are in balance, the resultant force is 0, so there will be no longer any acceleration. The person stops speeding up and we get this flat section of the graph. We call that terminal velocity. When the parachute is opened, there's a large upward force, okay, because the drag increases, because the air resistance increases. We've got a much bigger surface area, we're hitting more particles, there's a large upward force, that causes the person to decelerate. Doesn't make them go up, it makes them slow down. Okay? As they slow down, that drag force will start to reduce. Once it equals the weight again, the resultant force will be zero. They will reach a new but much slower terminal velocity, so they can safely land and not get hurt when they hit the ground. Okay, now it's important that we know what's happening in terms of the forces here and what's happening in terms of the motion. AQA love questions like this because they're asking you more than one thing at once. They're asking you to describe motion in terms of graphs and asking you about Newton's laws and about acceleration. Okay, so they really do like these questions. I think there's a good chance of something like this coming up. Okay, now that brings us to Newton's laws. I would like you to try and pause the video here, fill in the missing words about Newton's first, second and third law. Okay, moving on. Newton's first law. Okay, if the resultant force on an object is zero, then the object will stay stopped or continue to move at a constant velocity. If there's no resultant force, there's no acceleration. Okay, it will stay at rest, okay, unless acted upon by a resultant force. Okay, second law is describing how the force, mass and acceleration are linked. Okay, you can quote the equation: force equals mass times acceleration. If the resultant force acting on the object is increased, then the acceleration will increase. If the mass of the object is lower, the acceleration will increase. Okay, so acceleration is directly proportional to force, but inversely proportional to mass. The third law, okay, is whenever two objects interact, they exert equal and opposite forces on each other. That's telling us that forces come in pairs. Okay, so the gravity on this satellite, it's showing a weight arrow pushing down, but there's also a gravitational force pulling the Earth towards the satellite, and they are equal and opposite. Okay, now using those ideas, I would like to try and fix the mistake in this question. So pause the video here and try and fix the mistakes. Okay, moving on. So first, the person is swimming, they're not stopped. I know they're not stopped because there is a drag force. Okay, the key thing is the resultant force is zero, therefore there's no acceleration. It's not stopped, it's stopped or moving with a constant velocity. Now in this case, the person is swimming and they will be swimming so at a constant velocity. Okay, what's happening in terms of the force A and force B and the motion of the man is a little bit more tricky to get. This is incorrect. Okay, what we want is the man is moving at a constant velocity. The man will accelerate when force A gets bigger. Okay, there's an unbalanced force, there is a resultant force, so the man will accelerate. That causes force B to also increase until it equals force A. Okay, therefore there'll be a zero resultant force, so the man will be moving at a higher constant velocity. This is a question on terminal velocity. Terminal velocity does not need to take place with a parachute. Okay, terminal velocity is only, okay, it's all situations where a drag force is changing. So that's when anything is really moving through a fluid, and that's a science fluid. That's not liquid. It's a gas or a liquid. So when an object is falling or moving through a fluid, drag force changes with speed. It can reach a terminal velocity. Okay, be prepared for terminal velocity questions that might not look like terminal velocity questions. So here I've got a situation where I can measure the distance in given amounts of time, and I can look to see if it reaches terminal velocity. Okay, just a ball bearing flowing through some water or some honey or some oil, and I can see and measure if it reaches terminal velocity. Okay, now next, moving on. Okay, more forces. Next question is about momentum. Okay, momentum is a tricky concept, and some of the maths gets a little bit tricky. Okay, be aware that we want to choose the correct equation from the equation sheet. If it talks about momentum in a question, there's a strong possibility that you need to use this equation. Momentum equals mass times velocity. Okay, there is another equation that uses momentum, but this is most likely to come up. Okay, we've got two answers. I want you to try and fix the mistakes. Pause the video here. Okay, moving on. So first, momentum is a vector. The direction matters. The direction matters. Okay, so this this calculation question, the momentum of the star here is wrong. They've got a negative velocity. Okay, they've got a negative velocity, so you need to be really careful on how we add them up. Okay, momentum is conserved. That means the total momentum before something happens, a collision or an explosion, those are the two situations you will get asked about, equals the total momentum after. Okay, momentum before equals momentum after. Okay, now in the calculation questions, the method is pretty much always the same. You find the total momentum before or after the collision. You know the momentum after, therefore you know the momentum before, or you know the momentum before, so you know the momentum after. Then you can calculate the thing you don't know, its mass or its speed. Okay, this question we're asking the speed. So first I find the momentum of player A, then I find the momentum of player B. Now notice, negative 505, we've got a negative velocity. That matters. I find the total momentum by adding them up, so I get 84.5. I don't get 1085. It's 84.5. I know the total mass because the two players stick together. Okay, they collide and move off together. So the total mass is just adding those masses together. Then I can resubstitute this into my P equals mv. My momentum equals 169 for my mass times by my velocity. I rearrange to get the velocity of 0.5 meters per second. Okay. Be careful with the direction of the momentum. Right, moving on. Next, we have a diagram showing a light spectrum from the sun and 4 other stars, A, B, C, and D. We've got 2 questions. I'd like you to try and not just fix the mistakes here. I'd like you to try and answer these 2 quick questions. I also want you to think about what's the difference between redshift and blue shift. Pause the video here. Okay, moving on. So the first one is C. C is moving away from the Earth, okay, because C is the only one that is redshifted. The light wavelength has been increased relative to the sun. These absorption bands are increased. Okay, B and D, they are both blue shifted. Okay, the next one, the star speeds, okay, B is less than D. This star is not moving as fast as D. We're comparing just B and D, so we don't need to worry about A and C. We're just looking at these 2. Okay, now B and D, they're both blue shifted, but D's blue shifted more. Okay, the more the light is shifted, the quicker the velocity, the quicker it's moving towards or away from us. Okay, A, the distance between A and our star is not changing, it's constant. This light hasn't been redshifted at all. Okay, right, next, looking at the Big Bang Theory. I'm going to try and fix the mistakes here. What's the correct answers? Pause the video now. And moving on, it's not the origin of the Earth. Okay, it's the origin of the universe. Okay, the redshift, okay, or discovery cosmic microwave background is important. It's not the only thing. It didn't prove the Big Bang Theory to be correct. It's evidence to support the Big Bang Theory. Okay, there's a distinct difference. Okay, it's evidence for it. It's not proved. It's evidence to support it. There's alongside other evidence like redshift. Okay, next question, another one on redshift. We've got a binary star system. I want you to try and find and fix the mistakes on these quite tricky questions. So the first one, you need to give a name for the effect shown looking at star A, and then we want to explain how this information here shows that we've got a binary star system. I want you to try and find and fix the mistakes. Okay, I'm going to move on. So the Doppler effect will get you the mark here. It will be better to write redshift, okay, but Doppler effect in this case is quite generously giving you the mark in the mark scheme, but redshift would be better. We've got quite a waffly answer here, okay, quite a waffly answer. This diagram isn't necessarily showing the situation of our planets accurately. Okay, we don't know where we are. We don't know if we're looking from the bottom here or from the side or from the top. So talking about the arrow showing the planets moving around this direction is a little bit cheeky. It's not right. Okay, so it'd be better to say star A is moving away from the Earth. Okay, we know that because it's redshifted. That comes from this first bit. Saying it's redshifted doesn't get the mark because it's the answer to this first part. Okay, so star A is moving away from the Earth. The light from star B is blue shifted, so it's decreasing wavelength. This means star B must be moving towards the Earth. Okay, so we're going to mark for moving away, for blue shift, and for towards moving towards the Earth. Okay, it's not enough to say just redshift of that first part. Next question, nearly done. We've got a question on pressure in fluids. Okay, I would like you to try and answer these questions. We're not going to do a fix it. I'd like you to try and answer the question. Okay, be aware that you need to choose the correct equation. I've highlighted the things I'm given, and I've highlighted where I can find them in my equation sheet here. Okay, it gives you a bit of a clue of what equation might be best to use. Pause the video here, see if you can get the answer. Okay, moving on. We've got hydraulics. Hydraulics is using liquids, using fluids to transmit force. And here it's a pretty simple substitution. The pressure equals force divided by area, north to the surface, and the area of the surface it's acting on. So we substitute in, we rearrange, we get a force of 1,540 newtons. Okay, next page. I want you to fix the wavelengths and amplitudes. Okay, none of them are correct, none of them. Find the mistakes, find the lost marks. Pause the video here, sketch a diagram and fix it. Okay, moving on. We've got, first, when you're drawing the wavelength, it goes from the peak to the next peak. Not halfway down the peak, it goes from the middle of the peak to the middle of the next peak. Okay, we're trying to get this consistent wavelength from a point on the first wave to the same point on the next cycle. Okay, so you can draw this second wavelength at the bottom here in green, but be careful if we're doing a cross where it crosses the equilibrium line. This is half a wavelength. The blue line is half a wavelength. So you need to extend it to the next point in the wave. That's the same. Okay, we've got amplitude. This time we go from the equilibrium to the highest point on the wave, the highest displacement. We're not going from the trough to the peak. Okay, so be careful in drawing the amplitude and the wavelength. Use a pencil. Okay, draw it accurately. Take your time. Okay, I would suggest it's best to draw wavelengths, if you're given the option, from peak to peak. I think that's the easiest way, so you don't get confused about how many times you need to cross across the wave. Okay, so next I want you to pause the video. I want you to label a diagram of a transverse wave and a longitudinal wave. What might these labels show? And moving on, we've got vibration at 90 degrees to the energy transfer. Energy transfer is from the left of the screen to the right of the screen. Okay, the vibration is at 90 degrees to that direction. Okay, bottom of the wave is the wave trough, top of the wave is the wave peak. Here we've got a longitudinal wave on a slinky where it's all squeezed together. That's a compression. Where it's spaced apart, it's a rarefaction. Okay, the vibration is parallel to the direction of energy travel. So longitudinal transverse waves. Next, our final part, we're looking at a 6-mark calculation question. This is quite a tough question. We need to figure out what equations to use. Now, there's a number of ways we can do it. Okay, there are a number of ways we can do it. There's a couple of ways we can go about answering this question. I think there's one way that's better than the others. Okay, again, I'm highlighting some of these equations. Think about why I've highlighted them. Okay, what equations are you going to use, and see if you can calculate the resultant force acting on this car. Okay, needed to accelerate this car at these speeds from 0.12 meters per second to 0.52 meters per second. With that acceleration, with that work done, what will be the resultant force I need to use? Okay, so pause the video here, see if you can calculate that question. Okay, moving on, we've got, first I would use these two equations. This I think is the simplest way of going about it. I'd use final velocity take away initial velocity equals 2 times the acceleration times the distance. That's the way I would go about it. I chose that way because I've got 2 different speeds. Okay, now you can use other ways to calculate it, but I think that's the best way. So I substitute those numbers into my equation. Okay, I've highlighted just to show you where they're going. I calculate and rearrange what my distance is 3.2 meters, and then I use my second equation. I know I need to use 2 because it's a 6-mark question. Okay, so I substitute my 3.2 into my work equals force times by distance equation. Okay, what I've calculated here goes into this equation. My joules is in my answer, it's in my my question, and then I get a calculated value of 0.15 newtons. Okay, it is a toy car. So that's the end of this little masterclass. I hope it's useful. I wish you the very best of luck for your final exam. By all means, I would like to hear about how it goes. Okay, I hope it's going to go fantastically well. I think you're going to smash it. Well done from getting through your GCSEs. Okay, best of luck, Year 11. Bye-bye.